Hello, my name is Eric Godden, and I'm a member of Mithril and the Ingenuity Labs Research Institute here at Queen's University in Kingston, Ontario, Canada. In this video, I will be talking about our paper, Robotic Characterization of Markerless Hand Tracking on MetaQuest Pro and Quest 3 virtual reality headsets. As someone who leverages virtual reality technology in their research, I recognize the growing capabilities of markerless hand tracking technology. In this example, I'm capable of teleoperating a robot manipulator connected through my virtual avatar, all without the need for external tracking. While this technology has great potential to enable more natural and meaningful interactions in virtual environments compared to controller-based interactions, accurately tracking dynamic hand movement remains challenging due to the hand's high dimensionality and susceptibility to self-occlusions. Despite the challenges associated with markerless hand tracking, we've already seen application in domains such as physical therapy and robotic teleoperation. Yet the true performance of these commercially available markerless hand tracking technologies are not well understood due to limited evaluations that rely on non-standardized methodologies. This represents a key limitation for future integration of this technology and could stand as a roadblock in one's development pathway if proper performance metrics are unavailable. This is why this research aims to develop a standardized characterization framework and undertakes a performance evaluation of the markerless hand tracking on two commercially available virtual reality headsets, the MetaQuest Pro and Quest 3. As there's a well-established body of research in relation to perception thresholds for delays in human-machine interfaces, it is essential for characterizations such as in this work to evaluate tracking performance in relation to these thresholds. This will allow developers to understand tracking's impact on user experience and to align the expected performance to the true performance of this technology. We propose a comprehensive framework to systematically evaluate the performance of markerless hand tracking on virtual reality headsets. By combining robotics, motion capture, and virtual environment rendering, this framework enables precise and repeatable measurements. The combined system is shown in the rendering on the left. A replica hand was outfitted with retroreflective markers that, combined with the motion capture system, served as the ground truth for our measurements. The framework evaluates performance through three tests. The tests evaluate performance in both static and dynamic conditions and also incorporates the visualization capabilities through the third test. Further details for each test follow. The performance of both the MetaQuest Pro and Quest 3 were evaluated using the developed framework. The first test evaluates hand tracking performance under static conditions, removing the influence of latency on measurement accuracy. This scenario represents the optimal tracking condition, as temporal factors are eliminated and the hand's pose remains constant between frames. A three-dimensional testing volume was defined by lateral and interior proximity to the headset with three vertical levels. Each vertical level is composed of 7 base positions, as shown by the figure in the top right. At each position, 7 rotations are further applied to the hand to provide evaluation in situations where the hand does not sit in a palm-down configuration, matching many natural hand positions. With 7 base positions and 7 rotations across 3 vertical levels, there are 147 total unique points within this test. Both the index tip and index knuckle were individually set as the tracking feature for each headset condition to compare the influence of different anatomical features on tracking performance. At each testing point, 2 performance metrics were calculated. The first, average Euclidean error, represents the positional error of the VR tracking as compared to the ground truth. The second, jitter, represents the average magnitude of frame-to-frame jumps in subsequent stationary measurements within the VR data, providing a measure of the noise experienced in the tracking data. The second test evaluates the tracking performance under dynamic conditions to evaluate the latency of the markerless tracking on each headset. Latency refers to the time delay between ground truth motion and when that corresponding motion is detected on the tracking system. Other studies have confirmed that VR system latency varies throughout different phases of motion, likely attributed to a motion prediction step common in modern hand tracking algorithms. To capture this variability and ensure a proper evaluation of latency is completed, 3 metrics are evaluated. The first, cold start latency, refers to the time delay of the onset of motion. The second, warm-up duration, represents the time required for the motion prediction to take full effect. The final metric, constant velocity latency, is the tracking latency after the warm-up duration, capturing tracking performance when the motion prediction is in full effect. To evaluate these metrics, 12 constant velocity trajectories are defined across 3 vertical levels, which have been slightly modified from the first testing volume. The modified testing volume was selected to facilitate smooth joint velocities across the trajectories and to ensure a clear line of sight was available between the hand and the headset. The trajectories each spanned 0.3 meters, had steady-state velocities of 0.2 meters per second, and experienced constant acceleration and deceleration periods. Data was captured from both measurement systems across each trajectory, and the knuckle was selected as the anatomical tracking feature. While the first 2 tests evaluate hand tracking performance across both static and dynamic conditions, another key consideration is the motion to photon latency. Motion to photon latency incorporates the visualization capabilities of the headset by evaluating the time delay between user motion and when that motion is displayed on the headset. This is a very insightful metric as it incorporates both the hardware and software performance into a single measure. To measure this latency, the 12 trajectories from the second test are used. However, at the midpoint of each trajectory, within each measurement frame, a trigger point is defined. Once each measurement frame individually recognizes that the hand has moved past the trigger point, for the VR frame, the headset display is colored, and for the ground truth, the robot's end effector light is turned on. We are then able to use a high-speed camera to record the time delay between when the ground truth and the VR systems pass their corresponding trigger points, which results in our motion to photon latency. A simple main effect analysis of the average results across the testing volume shown in the table on the left revealed that the Quest Pro exhibited significantly lower static positional error, but significantly higher jitter than the Quest 3 in their respective anatomical feature conditions. Additionally, the results demonstrated that the knuckle tracking condition outperformed the fingertip condition for both static positional error and jitter for both headsets. This reinforces that the knuckle is a superior tracking feature, likely due to the knuckle being less prone to self-occlusions experienced by the hand. The table on the right displays the static positional error and jitter for each hand rotation represented as an average across the testing volume. Statistically significant differences were not found for these results. The plots shown display the static positional error across the testing volume for each test condition. It is clear to see that the tracking performance under all test conditions depend on the proximity to the headset. Error was the lowest when the hand sat in positions with small lateral and vertical deviations from the headset. Error was most significant at extremes of the workspace, as these points served as a blind spot that occasionally experienced drops in tracking. Similar results are found for jitter. The figures on screen display example output plots for test 2, which illustrate how the tracking develops over the constant velocity trajectories. The plot on the left shows how the markerless hand tracking progresses compared to the ground truth motion capture system. Some key points to note on the plot are the delay in motion onset. This will be captured by our cold start latency, the initial increased latency at the beginning of the trajectory, as motion has just begun and the motion prediction has not taken full effect, and when the VR trajectory converges to the ground truth, demonstrating motion prediction is in full effect. The plot on the right shows the development of tracking latency across the trajectory. Note the corresponding key points within this plot. The results of this test confirm that latency varies drastically throughout different phases of motion. For both test conditions, the cold start latency is an order of magnitude bigger than the constant velocity latencies, emphasizing the important role of motion prediction within tracking algorithms. The motion to photon latency results, presented as an average across the testing volume, represents the best overall understanding of tracking performance. Between test conditions, no significant results were found. Both results, though, were below visual discernible thresholds, but it should be noted that when one standard deviation is considered, those thresholds are breached. To summarize our contributions, we developed a novel characterization framework for markerless hand tracking. We then applied this characterization framework for the evaluation of the onboard hand tracking on MetaQuest Pro and Quest 3 virtual reality devices. Thank you so much for listening. If you have further questions, feel free to reach out or check out our paper for all the details.